Let's take a look at another example of a hypothesis test involving two population proportions and independent samples. Again, this is similar to the exercises in section 11.1, number 17 to 20. In 2018, kinesiology researchers at Top Sprint, a shoe company, surveyed a random sample of 500 top sub-3-hour marathon runners with the question, do you regularly run barefoot when training for a marathon? 60 of the 500 top marathon runners reported that they did regularly run barefoot when running and training for a marathon. In 2020, the kinesiology researchers asked the same question to another random sample of 350 top marathon runners, and this time 56 out of the 350 top marathon runners reported that they regularly run barefoot when training for a marathon. Is there sufficient evidence at an alpha equal to 0.05 level of significance to conclude that the proportion of top marathon runners who run barefoot when training has increased since 2018? So in step 0, we'll summarize the information and identify any point estimates. This study was looking at two different samples of marathon runners, one sample from 2018, one sample from 2020. In the 2018 sample, 60 out of 500 marathon runners said that they trained barefoot, and in the 2020 sample, 56 out of 350 marathon runners said that they trained barefoot. And so the sample proportion of marathoners who trained barefoot in 2018 is going to be our p-hat1. So we'll do x1 divided by n1, work that out, and it comes out to 0.12. The sample proportion of marathon runners who trained barefoot in 2020, we'll call that p-hat2. So that will be x2 divided by n2. Work that out, and it comes out to 0.16. The 2020 sample proportion, 16%, is higher than the 2018 sample proportion, which is 12%. So that seems to support the hypothesis that the proportion of top marathon runners who train barefoot has increased since 2018. However, we will need to test whether the 2020 sample proportion, 16%, is significantly higher and therefore sufficient to support this particular hypothesis. Step 1 is to state the hypotheses. So again, this hypothesis is involving two proportions. We'll use P1 and P2 to represent them. In particular, P1 is going to represent the population proportion of top marathon runners who ran barefoot when training in 2018. P2 is going to represent the population proportion of top marathon runners who ran barefoot when training in 2020. And here are the hypotheses using symbols. The null hypothesis is that the proportion of marathon runners who trained barefoot in 2018 is just the same as the proportion who run barefoot in 2020. The alternative hypothesis is that the proportion who run barefoot in 2018 is less than the proportion who run barefoot in 2020. And this might seem a little bit strange because in the wording of the question, it says, is there evidence that the proportion of marathon runners who run barefoot when training has increased since 2018? And usually when you see that word increased or increasing or rising, you would think that has to do with the greater than symbol. But you want to pay attention to what P1 and P2 stand for. And that's why this says be careful. When you're doing this kind of hypothesis testing, you want to really pay attention to that P1 and the P2. So the question is asking, has the proportion increased since 2018? In other words, is the 2020 proportion greater than the 2018 proportion? But remember, the 2020 proportion is P2. So we're asking, is P2 greater than P1? And the symbol for that would be to have the inequality this way, so that the open side is on the larger side. So again, on the homework or test, you can just write the symbols, but here are the sentences for full clarity of the hypotheses. Step 2 is to check the requirements. I won't go through these requirements in detail in this lecture, but they're all written in these notes in case you wanted to look them over. Step 3 is to test the hypotheses. And we'll go over the first approach, which is the classical or test statistic approach. We'll start by sketching out the normal probability curve, and then use table 5C to find the cutoff value for the region of the curve that represents unusual study outcomes. This is a left-tail test because of our alternative hypothesis, and alpha is 0.05. That's the area under the left tail of the curve. Here's a drawing of what that would look like. We'll go to table 5C, look up left tail test and alpha of 0.05, and that's negative 1.645. So that's our cutoff for that tail. The next thing is to calculate the test statistic. The test statistic is a z-score, and again, here's the formula for that test statistic. For that formula, we'll need the p-hat1, the p-hat2. Those we calculated earlier as being 0.12 and 0.16. You also need the pooled estimate, that p-bar. Use this formula. We'll put those values into the formula, and it comes out to 0.1365. So now we'll put in those values into this test statistic formula. Here's the P1 hat, P hat 2, here's the pooled estimate times 1 minus the pooled estimate times the square root of 1 over n1 plus 1 over n2, and this one comes out to negative 1.6719. So finally we want to determine whether our test statistic is inside the critical tail or outside the critical tail. And this time our test statistic is inside that critical tail. Here's the cutoff at negative 1.645, and this is just to the left of that. It's a little bit smaller, so it is in that left tail. So it's inside the critical tail, and that means that this study's results are unusual and significant, and will reject the null hypothesis. Method 2 is to do the p-value approach. And if you were doing this approach, you would use your calculator. Very similar to that first example we saw, you would take these steps on the Casio to get to the function called 2p. Put in the values for your inequality for the alternative hypothesis. Put in your x1, n1, x2, n2. Similar for the TI 83 and 84 calculators. Ultimately, you want to get to the 2-prop z-test. Plug in the values for x1, n1, x2, n2. Put less than here. And the p-value comes out to 0.0473. And so the meaning of that p-value is it's the probability that barefoot training would be reported by 60 or fewer out of the top 500 marathon runners in 2018. And that barefoot training would be reported by 56 or more out of 350 top marathon runners in 2020, assuming that the null hypothesis is true. But again, the main thing to keep in mind is that a p-value is the probability of getting that particular result from a study. And the last thing is we'll want to compare our p-value to the level of significance. For this study, our p-value is 0.0473, the alpha is 0.05, so our p-value is less than alpha, And since the p-value is less than alpha, that means that this study's results are unusual and significant, and we would say that we reject the null hypothesis. And the last step, state the conclusion. Remember that you want to state the conclusion in terms of whatever your alternative hypothesis was. So here we reject the null hypothesis. There is sufficient evidence to conclude that the proportion of top marathon runners who run barefoot when training has increased since 2018.